Well, let's continue and uh, let's try to go through
The contour lines on topographic maps like this one indicate slope and elevation. In this five-part video series, we'll explore the tools and methods used to determine elevation. I'm Todd Horton for the Illinois Professional Land Surveyors Association. For example, in modern agriculture, we can produce efficient,
here
reliable systems.
they explain
You learned
the purpose
is the
of
ratio
leveling.
of rise over run. Rise is a change in elevation, that is a vertical distance, and run is a horizontal distance. Measuring horizontal distance is simple with a tape or with a measuring wheel.
While
But how can we measure the
making
vertical distance? That is,
leveling,
the
we
rise between
just
the points
should
here. Well, that vertical distance is best found by a process we call leveling. To most people,
understand
this is a level.
what does it mean leveling.
More specifically, this is a carpenter level. It has a bubble tube that indicates which end of the level is higher than the other. Well, how does it do that? You see, the bubble moves in a curved tube like you see here. That's a very flat
Here they explain that
curvature.
bubble runs
As the tube tilts,
in a tube
the buoyant bubble
that
rises to
has
the highest possible position within the tube. Now, if I can hold the carpenter
the
level
form
steady
of circle
with
of
the
big
bubble centered
radius,
within the marks, both ends of the level will have the same elevation. Here you can
and
see
here we
that the
can
concrete surface
see
at this end is higher than the concrete surface at
the
the
difference
other
of
end the
heights
level. The underside of the level is now a
of
reference
these 2
line we can
points.
use. With the bubble centered within the marks, I can measure down from the underside of the level to the concrete. This measurement is 0.18 feet. Since the other end of the level sits on the concrete, the vertical distance between the two ends is 0.18 feet. By repeating
Here
this process
they
over
explain
and over, adding
how
measurements
can
end to
we
end, we can find the vertical distance between two distant points. But that becomes
measure
very
the
impractical as the horizontal distance increases. So, instead,
difference,
for leveling survey,
height
we
difference
use instruments like these.
between 2
This
points.
is an optical level.
Uh,
It's basically a telescope that can be oriented to create
here you
a
can see
horizontal
the
or level line of sight. Well, how does that work? The level
different
telescope
level equipment.
contains a crosshair. The horizontal crosshair defines a level plane in all directions. That is, your line of sight through the horizontal crosshair is a level
The line of sight
perpendicular to gravity.
in the
Just like the underside of the carpenter level was held level just a few
telescope
moments ago,
diaphragm.
now your line of sight is level. Because the optical level is telescopic,
Well, the optical
you can
level
see farther.
allows us to
If you can see farther,
make
then the distance between
the
your
measurement
locations can grow.
and
To measure elevation difference with an optical level, we also
measure
need a level rod.
elevation
This one is
differences.
graduated in decimal feet
Here
upward
you
from
see
0 and
aluminium
above.
rod
The difference in two rod readings taken from the same instrument location
and
equals the
the
elevation difference.
elevation
Now
differences.
here are some examples of optical levels. This dumpy level was made around 19.
It is an example of ancient instrument
Using the four adjusting
Uh,
screws in the instrument base, a surveyor would level the instrument in two directions, centering the bubble in its cylindrical tube. The tilting level represented the
Алло?
next generation of leveling precision. This one was manufactured in the 1940s. As optical science had improved, it
You
sported a
see
shorter
that the
telescope, and it had an innovative feature that allowed more precise leveling: the split bubble.
bubble
Below
tube
the long bubble tube,
is big enough
an adjustable mirror reflects light
to
into the fluid and bubble in the cylindrical
establish
tube.
the
Using a separate eyepiece and another internal
line
mirror,
of sight very
the operator
precisely.
views two halves of the bubble image and adjusts
Here
the
you can
level
see the
carefully to align the two images.
tilting level.
Introduced in the 1950s, the
Uh,
automatic level contains a
it
set
is
of tiny mirrors that move automatically in response to Earth
automatical level with
ensuring
mirrors
that the
inside.
instrument line of sight is perfectly level. If the instrument settles during use, this automatic
We
compensator
can see the
simultaneously adjusts
bubble
the line of
movement
sight
through the
back to
mirror,
the horizontal plane.
and while
You
the
can see the top of the mechanism moving.
bubble is the 0 point,
Because
the
the
compensator
compensators, automatic levels can give
automatically
greater precision than
establish
older,
the line of sight
uncompensated
in the horizontal
With the advent
position.
of inexpensive
Here you can
laser
see
devices,
the digital,
the rotary laser level has
modern
made some
digital level
leveling surveys possible
that
with only a single surveyor. A revolving mirror produces a horizontal plane
allows
of laser light. A laser
anybody
detector on a special
to
leveling
do
rod
the
enables
leveling
measurement at each desired location.
himself
Farm
without
drain tile installation equipment commonly uses a laser
any
plane
help.
to control the pipe
And
depth,
here you can see
ensuring
the
proper slopes and
special
efficient drainage.
construction
For
equipment.
high precision, digital levels with advanced internal compensators read the barcode on a special rod while simultaneously collecting
Special
atmospheric
rod.
pressure and temperature readings. Each of these methods creates a horizontal or level line. Using this line,
Well, each level equipment allows us to establish the line of sight in horizontal position, and so
with a telescope or with a focused
calculate
beam laser ray,
the
we can extend that line
elevation
much
differences
farther
between 2
with greater
points.
precision.
We can
So
see
far, you've seen the main tools we use
the
for
reading.
leveling. In the next video, we'll explore the basic processes of a leveling survey. I'm Todd Horton for the Illinois Professional Land Surveyors Association.
Well, and the next short video explains us how can we make the leveling procedure. Also, the video is very short.
Equipped with a leveling rod and an instrument, we can measure elevation differences. In this video, we'll explore the basic field processes involved in
I will switch
measuring
subtitles on
and then computing
so you can read the text.
for the Illinois Professional Land Surveyors Association.
Using an optical level, we create a horizontal line of sight. Where our line of sight intersects the level rod, we take rod readings.
Our line of sight intersects the rod. We take the rod readings
With practice,
and compute
most
elevation
instrument
differences
operators
with
can confidently read the rod when it is 250 feet away. Thus, if I need to find the rise between two locations 500 feet apart, I simply set up halfway between the points and take two readings. But what if I can't see between
Well,
those points? For instance, in this scenario,
when
the elevation
the slope
difference is greater than the height of my
is
tripod. Or what
very
if
big.
the locations are 5,000 feet apart? Well, to overcome these obstacles, we perform a level circuit. We perform a level circuit by measuring a series of elevation differences end to end.
Yes,
In the first
series
video, we
of
illustrated
elevation
concepts
differences.
with the carpenter level, but now we do the same process on a grander scale with an optical level. To find
And
the
here we
elevation
can
shown here on
calculate
the right, we
unknown
must first start
elevation
from an elevation
of
that is known, shown
landmark.
on the left. An elevation is a vertical distance above or below a reference surface.
We use
The combination
reference
means
surface
sea level
of
to reference
different
surface.
seas
The
in different
summit
countries.
of Mount Everest is 29,029 feet above mean sea level, and the lowest point in the United States is Death Valley at 282 feet.
Here is example of the lowest
By
place
measuring
in the
vast
United
networks of
States.
level circuits across the continent, surveyors have established heights above sea level as
Here
stable,
you can see the
permanent
level
benchmarks.
network of the United
Benchmarks
States
come in
and
many
the
forms and are attached to
benchmarks
everyday
on the
objects
different
like bridges and fire
buildings
hydrants.
and
Let's walk through a typical level circuit we call benchmark leveling.
elements of landscapes.
You may hear this process called differential leveling or control leveling as well. Here, our survey site is 1/2 mile from the nearest benchmark.
Benchmark leveling
We need to determine the elevation of a newly constructed benchmark on the site
from
because of the terrain and
the
distance
point with known
involved.
elevation to the point from unknown elevation.
Measure a series of elevation differences, feet. Since deviated as
Here
line of height is 4.69 feet above the elevation of 842.17.
backside
Thus, the HI of the instrument
reading on a point of known elevation
is 842.17 feet plus 4.69 feet, which equals 8. And the backside reading of the instrument operator toward the survey site. At a convenient location where the instrument is visible, the rod person will create a turning point. A turning point is a temporary intermediate point in a level circuit that we use.
here is a turning point in
This
English.
turning point must be stable and have a distinct peak or high point on which the rod will rest. Here, the rod person is using a cold chisel driven firmly in the ground. When it is stable, its top can have only one elevation. This
We can put
concrete
our
curb
rod
has high
on
spots
the
that make
concrete
the turning points.
elements of
And
construction.
this sidewalk
Just
will work too.
draw a cross
The
or
rod person
another
will
sign
top turning point 1
on
labeled
the
here as TP1. The instrument
for
operator
mark
can
our
make
turning
another
point
rod
1
reading called a foresight, commonly abbreviated as FS.
and foresight
Foresight
is
is
reading
taken
on a point of unknown elevation.
Reading at turning point 1, 6 feet, and since the we'll subtract 840.1 at a new the instrument and take a new
And at least we have
reading on a point of
um,
1 has a known
gather
2-point elevation
a number of readings
that
on every station,
convenient location will be
and while summarizing all these readings, all these differences, we can calculate the total
and efficient.
difference of elevations
In the
between
next
2
video,
points.
I'll show you how to prevent mistakes, how to record your readings, and how to compute with confidence. I'm
Well, speaking about leveling, we should distinguish optical leveling, which use kind of optical levels. Another option is trigonometric leveling. We use theodolite or electronic tachyometer. This is done by using total station or any instrument to rate the vertical or zenith angle to the rod and the change in elevation is calculated using trigonometric functions. At a greater distance, 1000 feet and greater, the curvature of the Earth and the refraction of the instrument wave through the air must be taken into account in the measurement as well. Here you can see an example. Instrument and point A leading to a rod at point B, and a zenith angle is 88 degrees, 15 minutes, 22 seconds of arc, and a slope distance of 305 feet, not factoring rod or instrument height, would be calculated thus. And here you can see the calculations. The elevation differences is somehow about 9.30 feet. Measuring an elevation change of approximately 9.30 feet in elevation between points A and B. So if point A is at 1000 feet of elevation, that point B would be approximately 1009.30 feet of elevation. As the reference line for zenith angles is straight up going clockwise, one complete revolution, and so an angle reading of less than 90 degrees would be looking uphill and not down. Here you can see the examples of refraction and curvature calculation. So we use a huge amount of instrument, for example, classical instrument Dumpy level, automatic level, and laser level. Here we will continue our explanation with precise digital leveling. And what does it mean, and how does it works? How does it work? Precise here you can see how we can use this instrument to measure the height differences above geoid surface. The geoid or sea level is the main geopotential surface, and also we have a number of geopotential surfaces above sea level and below sea level. The relationships between the ellipsoid surface, various geopotential surfaces, dashed blue, and geoid solid blue. The geoid exists approximately at mean sea level, not shown is the actual surface of the Earth, which coincides with mean sea level, but it's generally above the geoid. While measuring the elevation differences above sea level, we use so-called orthometric heights. Here you can see the geopotential surface or level surfaces, and we just put our instrument in between these points and measure the elevation differences, and in every case we put our instrument rotation axis parallel to the plumb line in every point. However, level surfaces are not parallel, and plumb line is also not has its own orientation in the space because of differences in the geological formations below this particular place, and so while doing optical leveling, we just can measure orthometric leveled heights between these level surfaces. You can see in the picture. However, it should be mentioned that we use different kind of datums, different kind of vertical datums. Tidal datums that is connected with tide measuring points that measure sea or ocean level. Orthometric datums that is established using the optical leveling, and 3D datums, for example WGS 84 and North American datum 83 or 86. These datums can be are established using satellite geodesy. Here you can see the differences or relationships of vertical datums for Tampa Bay in the United States between or among these different vertical datums. So, higher geodesy specialists, higher geodesy staff calculate the corrections between or among these different leveling observations. Here you can see the explanations of all the errors. the rotation axis of the instrument and axis of every leveling staff or rods. Shorten setup distances, instrument to rod, balance setup, minimize differences, observe over similar surface. When we are crossing the highway, we should avoid this kind of instrument and staff place. We just need to minimize dissimilar backside, foresight, observing conditions. You can see that in this case the crossing the highway with leveling line make much more smaller errors than in this case. Systematic effect of plumbing error and scale errors is small on flat terrain. Well, it means that sometimes we cannot establish every rod in a true vertical position. Systematic effect of plumbing error accumulates on the sloping terrain since B1 not equal to F2. B means backwards direction and F means forward direction. And every time going up the slope, the mistake or the error on the rod, back rod, will be greater than to the front rod. Also, we just need to use leveling bubbles onto high precision INVAR level rod. And we just can see if the rod is not vertical, while crosshair and edge of rod are not aligned. Rod scale correction. We have been spoken about this kind of error. Sometimes we just need to measure an average length excess of the rod pair in millimeter per meter. Length excess is determined in rod calibration process. Here you can see the rod calibration INVAR to bottom reference plate. So the zero number of this INVAR rod must be on the bottom reference plate. Here you can see unusual picture on a rod. This kind of code rod we use with digital leveling equipment, which need know our one person reading the and writing down all the readings of the rod. The instrument reads the reading itself and write all the readings into its own digital memory. Here you can see calibration report of a rod in metrology laboratory. Calibration temperature certificate, certificate of calibration, and etc. etc. Technical University in Munich, Stanford Liner Accelerator Center, and so on. Well, footplate of both rods. You can see that footplate should be really plain and must not have any defects. Critical distances, it's already well known in the metrology community that digital levels give accurate results at certain distances. Therefore, the expansion of these distances have to be evaluated to avoid them during the field measurements. As an example, measurements at and around a critical distance are shown below. Here you can see critical distances 13.15, 13.35, and 13.35 meters. And then Hans rule, keep all three crosshairs on INVAR. While the shoulder of a station, while a shoulder of a station is big, sometimes the elevation differences is also big, and we try to measure on the very end of the rod. It's not good idea, so the rule is to keep all three crosshairs on INVAR on the surface when we can make measurements. Another option, maintain line of sight half of meter above ground. Illumination of the rod with the angle of illumination as depicted in picture, wrong readings would be achieved. With the illumination as in the picture B, the illumination did not cause wrong readings. Then another way to make the measurement more accurate is rod temperature correction. Here you can see the equation with mean observed temperature of inverse strip, standardization temperature of inverse strip, and observed elevation difference between the benchmarks and mean coefficient of thermal expansion. So we use these coefficients to make our measurements more precise. We use special equipment thermistors for refraction correction. Refraction error does not cancel on sloping terrain warm temperature, as we have spoken above. Well, here we can see digital temperature readout for top and bottom temperature probes. So this equipment allows us to measure temperature on the instrument level and near the Earth's surface. The aspirated temperature probes consist of concentric cylinders, fans, and thermistor located at 30 centimeters and 130 centimeters on the tripod. So these temperature measurements allows us to avoid refraction error. Here you can see rigid leg tripod with thermistor equipment. Thermistor is a semiconductor type of resistor whose resistance is strongly dependent on temperature, more so than in standard resistors. Here you can see a refraction correction predicted because of temperature measurement. Astronomic correction. Here you can see very sophisticated one of several corrections applied to precise leveling. It's a kind of tidal deflection, epsilon on a section of length and direction S. Well, it's very sophisticated technique, which means the changing the elevation difference because of maximum tide. So when the sun and moon is situated in one proper place, the tide begins, and this tide changes the reference surface, and so the leveling rod, while the leveling rod goes in the direction to the maximum tide level, we should also calculate tidal deflection. Level collimation correction, confirmation and error in radiance. Well, we can use this collimation error while the instrument is not standing in the middle of the rods. Arthometric correction. backside, foresight. Well, that's all.